Ask anyone, what is time? Most people will say something like this. Time flows from the past into the future. It's the same for everyone. It has a now, and it moves forward on its own, unaffected by anything in the world. All of these assumptions sound reasonable. They even feel obvious. But here's the problem. All four of them are fundamentally wrong. Physicists of the past tried to verify these ideas and arrived at conclusions far stranger than most people expect. We tend to imagine time as a river that flows from past to future, sometimes faster, sometimes slower, but always in the same direction. The past feels fixed. Causes come before effects. A glass shatters, but the shards never reassemble. We remember yesterday and make plans for tomorrow. Time, to us, is an arrow with two very different ends. But the river metaphor raises deep questions. What exactly is flowing? What makes the past different from the future? Why does one feel closed and the other open? Physics has wrestled with these questions and reached a surprising result. The difference between past and future, between cause and effect, memory and expectation, does not appear in the fundamental laws of nature. Every major physical theory discovered in the 19th and 20th centuries, from Newtonian mechanics to quantum theory, is time-symmetric. If a sequence of events is allowed by the laws of physics, then the same sequence played backward is also allowed. There is only one exception: heat. It all began in 1824 with the French military engineer Sadi Carnot. He was obsessed with steam engines, the cutting-edge technology transforming the world. And he was annoyed that British engines were far more efficient than French ones. Carnot set himself a goal: understand the maximum possible efficiency any engine could reach. He wrote a small book, Reflections on the Motive Power of Fire. The book contains many mistakes. Carnot treated heat as a kind of fluid that produces work as it falls from a hot object to a cold one. But his central insight was correct. A heat engine works only because heat flows from hot to cold. Carnot's treatise eventually reached Rudolf Clausius, a famously rigorous professor. Clausius grasped the essential idea and gave it its first modern formulation. If nothing else changes, heat cannot spontaneously move from a colder body to a hotter one. Everyone knows this intuitively. Drop a hot metal ball into cold water, the temperatures even out. The ball cools, the water warms, the reverse never happens. Clausius's law is the only fundamental law in all of physics that distinguishes past from future. No other law does this. Not Newton's laws, not Maxwell's equations, not Einstein's field equations, not the equations of quantum mechanics. In every one of these frameworks, there is no built-in difference between past and future. The theoretical physicist Carlo Rovelli, a leading expert on quantum gravity, writes about this in his book, The Order of Time. If a sequence of events is allowed by the equations also allow the same sequence played backward in time. In the elementary laws of the world, the arrow of time appears only when heat is involved. The link between heat and time is extraordinarily strong. Wherever a distinction between past and future emerges, it is due to heat. In every phenomenon that looks absurd when played in reverse, something is being heated. If you watch a video of balls rolling across a table, you can't immediately tell whether the video is playing forward or backward. Either direction looks plausible. But if the balls slow down and come to a stop, the illusion breaks. Now you know the video is playing forward, because in reverse, the balls would start moving on their own, which is impossible. The balls slow down because of friction, which produces heat. And it is only because heat is generated that we can distinguish the past from the future. Even your own thoughts move from past to future, because every neural impulse produces a tiny amount of heat. Clausius introduced a quantity to measure this irreversible flow of heat. Entropy, from the Greek word meaning transformation. Entropy is measurable and calculable, and it's denoted by S. Entropy can increase or stay constant, but in an isolated process, it never decreases. In equation form, delta S is always greater than or equal to 0. This inequality is the second law of thermodynamics. It is the mathematical expression of the arrow of time. The entire structure of the physical world is hidden in this one statement. Many physicists consider the second law the most reliable law in all of science. If you had to guess which modern physical principle would still be valid 1,000 years from now, the second law would be a safe bet. Arthur Eddington, one of the most influential astrophysicists of the early 20th century, put it this way: if someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. The story of the second law of thermodynamics leads to a romantic figure with a tragic fate, Ludwig Boltzmann. He was short, round, and forever disheveled. His daughter affectionately called him a sweet, kind, fat man. He swung between excitement and deep depression, moved restlessly from city to city, and joked that his instability came from being born during carnival. Boltzmann realized something revolutionary. Heat is not a fluid. It is the collective motion of molecules. In hot tea, molecules vibrate violently. In cold tea, they move more slowly. In an ice cube, they barely move at all. In the late 19th century, many scientists believed molecules and atoms were imaginary. But Boltzmann was certain they were real, and he fought relentlessly for this idea. Just as Copernicus looked at a sunset and sensed the Earth rotating beneath him, Boltzmann looked into a cup of tea and sensed atoms in motion. The molecules inside are in constant revolt. Then there are multicellular organisms on Earth. This chaos mixes everything together. If some molecules slow down, others immediately jolt them back into motion. Because of this, cold tea will heat up when it touches hot tea. The fast molecules collide with the slow ones and mix them like shuffling a deck of cards. When cards are arranged perfectly, say 26 red on top, 26 black below, shuffling destroys that order. That is how heat transfers from hot to cold, by mixing, by breaking down order. This was Boltzmann's insight. The difference between past and future is not written into the fundamental laws of nature. It emerges from the natural tendency of ordered states to become disordered. But then, a deeper question appears. Why was the world ever ordered to begin with? Why was the cosmic deck of cards arranged in a special, low-entropy configuration? Because if a process starts in low entropy, it is obvious why entropy increases. Shuffling destroys order. But a deck is special only because we choose to track color. Another ordering might be special by some different criterion. Every configuration is special by some definition. Every child is unique in a mother's eyes. Boltzmann realized that entropy counts the number of microscopic configurations we would consider the same when we look at the world in a blurred, approximate way. Heat, entropy, the low entropy of the past. These appear only when we describe nature statistically, not microscopically, which leads to a disturbing question. If we could track every microscopic detail of the universe, would the flow of time itself disappear? Yes. If I observe the microscopic state of affairs, the difference between past and future disappears. The future of the world, for example, is determined by its present to no less or more a degree than its past. We often say that causes precede effects, but in the elementary grammar of things, there is no difference between causes and effects. There is a certain regularity dependent on what we call the laws of physics, which determines the connection between events related to different moments in time. But this regularity is symmetrical with respect to the interchange of past and future. In a microscopic description, there is no way to distinguish past from future. This is the disconcerting conclusion that follows from Boltzmann's work. The distinction between past and future is a consequence of our unfocused view of the world. The conclusion is terrifying. Could it be that my so vivid, existential, all-encompassing sense of being and the passage of time is explained by the fact that I cannot see the world in all its minute detail? Is it simply some kind of error due to my myopia? Surely, if I clearly saw the dance of billions of molecules, would the future be the same as the past? Would I be equally aware or unaware of the past as I am of the future? I agree that our intuitive perception of the world is often mistaken. But could the world really be so fundamentally different from our intuitions? All this undermines the foundations of our usual understanding of time. It provokes complete mistrust. But the arguments are inexorable. All phenomena characterizing the flow of time are reducible to a special state of the world in the past, a specialness that lies in the defocus of our vision. Boltzmann understood something even deeper. Entropy is simply the number of microscopic states that our blurred, unfocused perception cannot distinguish from one another. The formula expressing this insight is carved into the marble of Boltzmann's tomb, right above a bust, portraying him as stern and severe, which he never was. Boltzmann became a professor at 25 and was welcomed at the imperial court. but the scientific community failed to grasp his ideas and attacked them harshly. Caught between bursts of elation and episodes of crushing depression, the sweet, kind, fat man, as his daughter called him, took his own life. He hanged himself while his wife and daughter were swimming in the sea. With Boltzmann's work, time lost its first great foundation, the intrinsic difference between past and future. He showed that nothing in the fundamental workings of nature creates the flow of time. What we experience as time's arrow is only a faint trace of a special condition in the universe's distant past. Now, it's time to examine the other three ideas we take for granted. Here is a simple fact. Time moves faster in the mountains and slower in the valley. The effect is tiny, but measurable with precision clocks you can buy today. Even a vertical difference of a few centimeters is enough. A clock on the floor ticks a little slower than a clock on a table. And it's not just the clock. Everything slows down. Aging, heartbeats, atomic vibrations, the very passage of time itself. Counterintuitive? Yes, but that is how the universe works. Einstein predicted this effect a century before anyone could measure it. He sat, thought, did the math, and understood. That is the essence of science. Anaximander understood that the Earth hangs freely in space long before anyone circumnavigated the globe. Copernicus realized that the Earth rotates long before anyone reached orbit. Einstein realized that time flows differently in different places long before we had clocks capable of detecting the difference. Each of these discoveries teaches the same lesson. What feels obvious is often just superstition. Einstein once asked a simple question. How does the sun attract the Earth if they never touch? He proposed that a massive body changes something around it. And since a body is surrounded only by space and time, it must be time itself that is altered. The Earth slows down time around it. Time runs slightly slower in a valley and slightly faster on a mountain, because a mountain lies farther from Earth's center. Objects fall not because an invisible force pulls them, but because time flows more slowly lower down. Things move toward where time flows slowest. Your feet remain on the ground for the same reason. They exist in a region of greater time dilation. Time ticks ever so slightly slower at your feet than at your head. But this creates a new problem. If time flows differently in different places, which time is correct? The clock on the table runs faster than the clock on the floor. Which one measures the true time? It turns out the question has no answer, because the question itself is meaningless. It's like asking which is more correct, the dollar-to-pound exchange rate or the pound-to-dollar rate. Neither. Only the relationship between them matters. With time, the situation is even more extreme. We don't have two different times. We have an infinite number. Every point in space has its own local time. There is no universal time at all. Einstein taught us how to write equations that describe how the proper time of one event evolves relative to the proper time of another. He showed us how to calculate the difference between them. A single concept, time, unfolds into a whole web of local times. We don't describe how the world evolves in time. We describe how things evolve in their own times and how those times relate to each other. The world is not a platoon of soldiers marching to a single rhythm. It is a network woven from events influencing one another. So time lost its second attribute, uniqueness. But what about its direction? Einstein made another discovery. 10 years before he understood how mass slows time, he realized something even stranger. Motion also slows time. Imagine a young couple. The girl stands still. The guy walks back and forth. For the one who is moving, time passes more slowly. He ages a little less. His watch shows less elapsed time. For anything in motion, time slows down. To see the effect, the speeds must be very high. It was first measured using atomic clocks on a jet plane. Physicists placed ultra-precise clocks on board, sent the plane around the world, and compared the airborne clock to one left on the ground. When the plane returned, its clock lagged behind by a few billionths of a second. Tiny, but exactly what Einstein predicted. The effect becomes dramatic at near light speeds. In the Large Hadron Collider, protons are accelerated to almost the speed of light. At that speed, time for them slows down by a factor of about 7,000. Another example, muons, unstable particles that normally decay in 2 microseconds. When accelerated to near light speed, their internal clock slows so much that they survive for about 60 microseconds 30 times longer. For the muon, only its normal 2 microseconds pass. But to an outside observer, the muon appears to live 30 times longer, moving in slow motion. Astronauts on the International Space Station experience two competing effects. At 400 kilometers above Earth, gravity is weaker, so their clocks run faster. But they orbit Earth at 7.66 kilometers per second, and this high speed slows their clocks down. The second effect wins. Over the course of 6 months on the ISS, an astronaut ages approximately 5 milliseconds slower than his twin on Earth. Over a career, the difference can add up to hundredths of a second. Small but real and measured with atomic clocks. Astronauts literally take a microtrip into the future. This effect is so real that we must correct for it in satellite navigation. Without adjusting for time dilation, the GPS or GLONASS receiver in your phone would drift by several kilometers every single day. Time dilation is not an illusion or a technical glitch. Time truly flows differently for objects in motion. It is a fundamental property of our universe. Einstein was only 25 when he realized this. He was studying Maxwell's equations, the laws that govern electricity and magnetism, and he noticed something strange. If you move fast enough, the equations no longer work for you. They describe the world perfectly, and they include a time variable t, but they have a peculiar feature. If you move at a certain speed, Maxwell's equations only work if you replace t with some other time variable. Mathematicians already knew about this odd feature of Maxwell's equations, but no one understood what it meant. Einstein did. T is the time that passes for me, standing still. T is your time, the rhythm at which events unfold for you as you move. T is the time measured by my stationary clock. T is the time measured by your moving clock. Nobody had imagined that a stationary clock and a moving clock could tick at different rates. Einstein saw this written between the lines of Maxwell's equations because he took them seriously. For a moving object, less time passes than for a stationary one. A clock ticks away fewer seconds. A plant grows less in size. A baby dreams fewer dreams. For a moving object, time shortens. Not only is there no common time for different places, but there is no single time even in the same place. A specific duration can only be associated with a specific movement of something, with a specific trajectory. Proper time depends not only on location, not only on the size of a nearby mass, but also on the speed with which we are moving. Again, there is no single time, even at a single point in space. Each trajectory has its own time, a very strange fact, but its consequences are even stranger. Take this question. What is happening right now on Proxima b? Imagine you have a brother who left for Proxima b 10 years ago. The planet orbits the closest star to the Sun 4 light years away. You ask, what is my brother doing now? The correct answer, the question, is meaningless. Picture your brother standing right in front of you. When you look at him, light reflected from his face has to travel to your eyes. That takes time, nanoseconds. You never see what he is doing now. You see what he did nanoseconds ago. If your brother is on Proxima b, light takes 4 years to reach you. Through a telescope, you will see what he was doing 4 years ago. Clearly, now on Proxima b cannot mean the light that just arrived. Fine, so maybe now means what he is doing exactly 4 years after what you see through the telescope. No, that doesn't work either. 4 years after you see that image, you might be 20 years older, or you might have traveled somewhere else. Nothing guarantees that this moment of your life corresponds to anything meaningful on Proxima b. Then what if your brother took a calendar with him when he left Earth? Could now simply be 10 years later on his calendar? No, again. 10 years after he left Earth could, for him, correspond to 20 years on Earth or 5. His proper time depends on his path through space-time. So when is now on Proxima b? Frankly, we have to give in. There is no special moment on Proxima b that corresponds to our here and now. Pause for a moment and let that sink in. To me, it is the most astonishing insight in all of modern physics. Asking which moment on Proxima b corresponds to my present moment is meaningless. It's like asking which football team will win the basketball championship or how much a musical note weighs. These are all meaningless questions because football teams play football, not basketball, and musical notes have no weight. The present is about what's close, not what's far. Our present doesn't extend across the entire universe. It's like a bubble surrounding us. The size of this bubble depends on how precisely we measure time. If we can distinguish nanoseconds, our present shrinks to a sphere only a few meters across. If we distinguish milliseconds, the bubble expands to a few kilometers. Humans perceive time in tenths of a second, so the entire Earth falls into a single bubble of shared now, but no farther. Beyond that bubble lies the past events that occurred before the light reaching us now. Ahead lies the future events we have not yet seen. Between them is a region that belongs to neither the past nor the future, an extended present. The idea of a single universal now is an illusion, an unjustified extension of our everyday experience. Like a rainbow that seems to rest on the treetops. From afar, the point looks real. Walk toward it, and it vanishes. A helpful analogy is family structure. You have parents and grandparents, your ancestors. You may have children or grandchildren, your descendants. But many people are neither your ancestors nor your descendants, cousins, colleagues, neighbors. You can't say that all these people belong to the same generation as you. The concept of generation works only partially. Family ties create a partial order. Ancestors come before you. Descendants come after you. Many others exist outside this line, neither before nor after. The temporal structure of the universe is built the same way. Every event has its own past light cone and its own future light cone. Between them lies a region that is neither past nor future. Special relativity teaches us that time resembles a family tree, a web of relationships, but not a single ordered line. We can no longer imagine the universe as a layered cake, with each layer representing simultaneous events everywhere. Such a global now simply does not exist. Thus, time loses yet another of its supposed foundations. There is no universal present. This is perhaps Einstein's strangest discovery. Instead of layers, the temporal structure of the universe is defined by light cones. Let's understand what these are. Imagine lighting a candle. A flash of light spreads outward in all directions, forming an expanding bubble. Nothing inside this bubble can outrun the light front. Doing so would require exceeding the speed of light. To visualize this more simply, imagine looking at only a two-dimensional slice of space. The expanding bubble of light now appears as a growing circle. If we stack all the moments of time together, this circle becomes a cone, a light cone, stretching from the past into the future. Our world line, our trajectory through space-time, must always lie inside it. The walls of this cone are tilted at 45 degrees. Why? Because in any given unit of time, light travels a fixed distance. 1 light year per year, 300,000 kilometers per second. Light cones define cause and effect in the universe. If a supernova explodes far away, that event cannot influence us until its light cone intersects Earth. Until then, no signal, not light, not particles, nothing can reach us, because nothing travels faster than light. Causality is limited by the speed of light. Light cones also reveal the difference between space and time. In space, we can move however we like, turn around, loop, wander. But in time, every object is forced to move in a single direction from past to future. There is no turning back. Light always follows these tilted lines, forming cones. Einstein realized this at 25. 10 years later, he discovered that the rate at which time flows varies from point to point. But he didn't stop there. If speed affects time and mass affects time, then these two influences must be connected. Einstein found the connection. Mass does more than slow time, it curves space-time itself. To understand how revolutionary this was, we need to go back into the history of ideas. Aristotle was the first to analyze the nature of time. He concluded that time is a measure of change. Things constantly change, move, grow, transform. Time is the language we use to describe when these changes occur. "I will return in 2 days" means the sun will cross the sky twice. But what if nothing changed at all? Would time still pass? For Aristotle, the answer was no. If nothing changes, there is no time. Time is simply a trace of motion. Isaac Newton argued the exact opposite. In his Principia, he separated time into two kinds. Relative time, the everyday time we measure with clocks, calendars, and motion of the sun. Absolute time, true, mathematical time, flowing uniformly on its own, independent of events. This absolute time is invisible to the senses. We know of it only through reasoning. Clocks are devices that attempt to track this universal flow. Two great minds offered two opposing ways to think about time. Aristotle said that time is nothing more than a measure of change. Newton claimed that there exists an absolute time that flows on its own, independent of anything in the world. So who was right? For several centuries, Newton seemed to be. Newtonian physics worked extraordinarily well. Its equations include the letter T time, and this T refers to absolute, true, mathematical time. The idea that time exists independently of things feels natural to us today. But that's only because we've learned it since childhood. It is not an ancient human intuition. It is Newton's invention. Before Newton, no one imagined time as something separate from the world. Einstein managed to reconcile Aristotle's idea with Newton's. His answer to the question, who is right, is yes. Time and space really do exist. They are real, but they are not absolute and unchanging, as Newton thought. They are made of the same stuff as everything else in the world. These substances that form the fabric of the physical reality of the world are what physicists call fields. Houses and stars are made of Dirac fields. The field, called electromagnetic, woven into the fabric of light. It is what makes electric motors spin and the magnetic needle of a compass point north. But there is also a field called gravitational. It is responsible for universal gravitation, but it is also the very canvas upon which the entire picture of Newton's world is painted. Clocks are mechanisms that measure its extension. Rulers are those fragments of matter with which we can measure another component of that same extension. Space-time is a gravitational field, and vice versa. It is something that exists in and of itself, including in the absence of matter. But this entity is no different from all other entities in the world. As Newton thought, it is a field, like everything else. The mutual influence of fields on one another is described by equations. Space-time is one of these fields. Space-time is a gravitational field. It is the canvas on which the picture of the world is painted. But this canvas is made of the same substance as the picture itself. The gravitational field behaves like an elastic fabric. Place a heavy ball on it, and the fabric bends. That is how massive bodies deform the space-time around them. Space-time can stretch and contract. Waves can ripple across it. Its curvature explains gravity and the falling of bodies. Clocks run slower near massive objects because space-time itself is stretched. There is literally less time there. In an empty universe with no gravity, the fabric of space-time is flat. Time and space form a smooth grid, and the light cones all point in the same direction. Time can be defined globally. On a diagram, it simply flows from left to right. But if a massive body exists, say, the Earth, everything changes. An apple falls downward under the influence of gravity. But gravity bends not only matter, it bends light. The expanding bubbles of light emitted by the falling apple tilt downward as well. Near a massive body, light cones are no longer parallel. They curve increasingly, distorted by gravity. When the direction of the light cones bends, it means that time itself is bending toward the center of the planet. The apple falls, even if it starts at rest, because its future points downward. Mass distorts the geometry of the universe. Space and time become relative. Their orientation depends on where you are. The more massive and compact an object, the more sharply it bends space-time. Now imagine an extremely massive and compact object. Its curvature becomes so intense that below a certain height, all light cones tilt fully inward. If you lit a candle there, every beam of light, no matter the direction, would head downward toward the center. This is a black hole. A black hole is a spherical region of space-time where curvature forces all trajectories toward the center. The boundary of this region is the event horizon. Above the horizon, some light rays can still escape. Below it, light is trapped. Inside a black hole, the light cones force every particle, every object, every signal to move inward. There, time itself points toward the center. When matter collapses to form a black hole, the light cones crossing its event horizon are turned inward toward the singularity. Inside the horizon, time still flows, but oddly, it flows in a direction you would consider spatial, toward the singularity at the center. To escape, things would have to move backward in time. To understand a black hole, we must look from two perspectives, that of an astronaut falling in, and that of a distant observer. For the distant observer, gravity is weak and space-time is almost flat. Time flows straight from left to right. The event horizon appears motionless, like a frozen boundary in space. For the falling astronaut, the picture is entirely different. As he approaches the horizon, he sees space-time bending more and more. When he reaches the horizon, space and time tilt at 45 degrees. For him, the event horizon is not a horizontal line across time. It is a diagonal line, slanted at 45 degrees, like the surface of a light cone. Crossing the horizon, the astronaut discovers that the meanings of time and space have flipped. Time now points downward toward where space used to point. Inside a black hole, the horizon is no longer a place in space. It is a moment in the past. And the center of the black hole is not a point in space. It is an event in the future. Below the horizon, every object must fall, because that is where its future lies. When a massive star collapses, it emits one final flash of light, a last expanding bubble that tries to grow, but is held in place by the immense curvature of space-time. A black hole is, in a sense, a light cone frozen by curvature. Once inside, nothing can avoid the center, the region where space-time becomes so warped that our physical models fail. In the debate between Newton and Aristotle, both were partly right. Newton was right to say that, alongside visible things, there exists a true time, a real physical entity. Today, we call it the gravitational field, the elastic fabric of space-time. But Newton was wrong to imagine this time as uniform and independent. Aristotle was right that when and where always refer to something else, some background structure. That something could be the gravitational field itself. Time lost its fourth attribute, independence from the world. It became woven with the geometry of space into a single dynamic fabric. Einstein wrote the equations of the gravitational field in 1915. But a year later, he realized this could not be the final answer. Quantum mechanics existed, and if everything in nature has quantum properties, then space-time must have them too. Time must have them. That changes everything again. Quantum mechanics is built on three profound discoveries: discreteness, uncertainty, and relationality. Each one erodes what little remained of our familiar idea of time. The first discovery, discreteness, granularity. Physicists discovered that time is quantized. It can take only certain values. It is not continuous. Every phenomenon has a minimum scale. For space, the minimum scale is the Planck length. For time, the minimum scale is the Planck time 10 to the power of -44 seconds. This is unimaginably small, far beyond the reach of any modern clock. At this scale, our everyday notions of time simply collapse. If a sufficiently precise clock existed, it would show that time takes only discrete steps like the rungs of a ladder. You cannot stand between them. Time does not flow smoothly. It jumps, like a kangaroo, from one tick to the next. There is a minimum interval. There is simply no time shorter than that. For centuries, philosophers debated whether continuity is real from Aristotle to Heidegger. Perhaps in vain. Continuity may be only a mathematical approximation of something fundamentally made of tiny, indivisible units. The world is not continuous. It is finely discrete. God did not paint the world with smooth strokes, but with tiny dots like Georges Seurat. Look around. Granularity is everywhere. Light is made of photons. The energy levels of electrons and atoms come in discrete packets. Even the purest air, like the densest metal, is granular, made of molecules. Once physicists realized that space-time is a physical field like any other, it became natural to expect that it too must be granular. Well, let's move on. The second discovery is uncertainty. Imagine a cat wandering around the yard. You can point and say exactly where it is on the porch, under a bush, on the fence. With elementary particles, this certainty disappears. Take an electron. You cannot say where it will be tomorrow, or even where it is right now. Not because we lack information, but because the electron is not in a single location. It is spread out like a cloud of possibilities, existing in many places at once. Physicists say the electron is in a superposition of positions. Space-time behaves in the same way. It fluctuates. It can exist in a superposition of different shapes and curvatures. Even the light cones that separate past, present, and future begin to wobble. The distinction between before and after becomes blurred. An event can occur both before and after another event, like a poorly tuned television where the image splits into two overlapping frames. The third discovery is relationality. Quantum fluctuation doesn't mean complete chaos. When an electron interacts with something, a screen, a detector, another particle, it collapses into a definite location, like a ghost suddenly becoming solid. But there's a catch. The electron becomes definite only for the object it collides with. For everything else, it remains a ghost. Think of an old cathode ray tube television. An electron slams into the screen and creates a tiny glowing dot, the image you see. But that definite impact exists only for the screen. To the person watching TV, or to the cat strolling by, the electron simply transfers its ghostliness to the screen. Now the electron and the screen together form a larger shared ghost. Only when that ghost interacts with something else does it become definite again. The same is true of space-time. The gravitational field is a quantum object with no fixed shape or duration. Only when it interacts with something does it produce a definite measure of time, and that duration exists only relative to the thing it interacted with. For the rest of the universe, time remains a hazy cloud of possibilities. The network of temporal relationships unravels. It no longer forms a dense, continuous fabric. Instead, we get overlapping superpositions of different possible spacetimes, like multiple exposures on the same photograph, faint images on top of one another. The picture is blurry, but this is all that remains of a world ground into quantum dust. It's hard to accept that an electron behaves so strangely, but it's even harder to accept that space and time behave the same way. And yet this is the world of quantum phenomena, the world we actually live in. The physical substrate that defines extensions and durations, the gravitational field, has dynamics dependent on masses, yet it is itself a quantum entity lacking definite numerical properties except during interactions. When interactions occur, durations and distances become granular, defined only relative to that interaction. For the rest of the universe, they remain undefined. The web of temporal relations unravels. It no longer forms a dense canvas. Before us lies the world of quantum gravity. Quantum gravity is something we still don't understand. General relativity gives a beautifully successful description of gravity as we experience it, but it is built on a classical foundation. In Einstein's theory, gravity is the curvature of spacetime, and in principle, you can measure that curvature with unlimited precision, but this can only be an approximation. We expect that beneath it lies a deeper theory, quantum gravity, in which spacetime itself is described by a wave function. A wave function is a mathematical object that encodes all possible states of a system at once. For an electron, it describes every location it might occupy. For the universe, it describes every way it might be arranged. Think of a deck of cards, shuffle it, draw a card, but keep it face down. Until you turn it over, the card could be anything. The wave function describes exactly that state of uncertainty, all possible cards at once. The universe works the same way. There is a wave function of the universe, a mathematical structure containing all possible histories, all possible configurations of matter, energy, and spacetime. Every version of reality, encoded simultaneously. But that leads to a strange question. If the universe is everything, then what does it interact with? In quantum mechanics, a system becomes definite only through interaction. But the universe has no external observer. There is nothing outside it that could collapse its wave function. So is the universe forever stuck in superposition? Do all possible versions of reality exist at once? Maybe they do. Maybe we live in just one branch of an enormous cosmic wave function, one of infinitely many parallel realities we cannot see. Now, consider two particles. Call them Alice and Bob. They meet, interact, and then drift far apart. They could be separated by millions of kilometers. And yet something remarkable happens. After their interaction, Alice and Bob remain connected by an invisible quantum thread. Measure Alice's state, and Bob's state is instantly determined even if Bob is on the other side of the galaxy. This does not transmit information faster than light. Instead, it means that Alice and Bob are no longer two independent particles. They have merged into a single quantum system. They share one wave function. Einstein called this phenomenon spooky action at a distance. He disliked it, but experiments have repeatedly shown that entanglement is real. Now, think about this. In the very beginning, during the Big Bang, everything in the universe was compressed into an unimaginably small region. Everything touched everything else. Everything interacted with everything else. Therefore, the entire universe is entangled. Every atom is linked to every other atom by invisible quantum threads. You are connected to distant stars, to rocks on Mars, to photons in distant galaxies, to everything that exists. Entanglement between two widely separated subsystems seems incomprehensible to us because it violates our intuitive idea of locality. Objects should directly influence only nearby objects, not those arbitrarily far away. Wave functions don't behave that way. There is a single wave function that describes the entire universe at once, and that's the end of the story. The universe is not a collection of separate objects. It is one indivisible quantum system, a single, giant wave function in which everything is entangled with everything else. And time? Time is simply a way of describing how one part of this system relates to another. When we say time flows, we are really talking about the evolving relationships between entangled parts of the universe. Time does not exist somewhere out there, independent of things. It arises from connections from the relations within a unified whole. There is no fundamental time, and there is no space as a static stage on which events unfold. There is only quantum entanglement, a vast web of interactions that is reality. And yes, our recent discussion about black holes is directly connected to this. Space-time ceases to be absolute. It can exist in different configurations, each with its own amplitude. So even the concept of distance between objects becomes slightly blurred. We still don't fully grasp such ideas. So how do we describe a world in which everything happens, but there is no single time? No universal rhythm? No privileged direction of change? Surprisingly, the answer is simple. It's the way we thought about the world before Newton. We don't actually need a time variable to describe reality. What we need are variables we can observe and measure. The length of a road, the height of a tree, the temperature of a body, the angle of the sun, the position of the moon. These quantities change, and we notice regular patterns. Stones fall faster than feathers. The moon and the sun meet every month. Some changing quantities repeatedly return to the same configurations. The phases of the moon, the number of days, the position of clock hands. They're convenient to use as reference cycles. So we agree on conventions. See you tomorrow at 5 o'clock at our favorite cafe. There is no need to choose one special variable and elevate it above all others as the time. All we truly need is an understanding of how different variables change relative to one another. In 1967, two physicists, Bryce-DeWitt and John Wheeler, wrote down the first equation of quantum gravity, an equation without the variable of time. Today, it is known as the Wheeler-DeWitt equation. At first, no one understood what it meant. Entire conferences were organized to debate it. Wheeler himself once said, "Explain time, impossible without explaining existence. Explain existence, impossible without explaining time." But when the dust settled, one conclusion became clear. There is nothing surprising about the absence of time in the fundamental equations. At the deepest level, a single time variable simply does not exist. The theory doesn't describe how the world evolves through time. It describes how things change relative to one another, how relationships form between events, how facts connect to other facts. The equations of loop quantum gravity are a modern descendant of Wheeler-DeWitt. They also contain no time variable. In this theory, fields exhibit granularity in the form of elementary quantiphotons, particles, and grains of space. These grains are not floating inside space. They form space itself. Space is nothing more than the web of their interactions. These quanta do not live in time. They continuously interact with one another. They exist only as endpoints of interaction. Each interaction is an elementary event, an elementary unit of time. The fundamental quanta of gravity exist at the Planck scale. Their relationships form networks called spin networks. These networks evolve by discrete jumps into higher dimensional structures known as spin foams. On large scales, this swarm of interactions looks like smooth spacetime. On small scales, it becomes quantum spacetime fluctuating, granular, endlessly buzzing with quanta that appear and vanish. Some physicists, among them Carlo Rovelli, are studying how long it takes for a black hole to explode during its quantum phase. Inside this phase, there is no single spacetime. The interior of a black hole becomes a quantum superposition of spin networks. Just as an electron is not at one point but spread across a probability cloud, a black hole in its final quantum state passes through a phase of time fluctuations, a state where time itself trembles, blurs, and dissolves into quantum superposition. For this intermediate phase, when time is completely undefined, we have equations that tell us what happens there. And in these equations, there is no time. This is the world described by loop theory. Am I sure this is the correct description of the world? No, I'm not sure, but it is the only consistent and complete way we know today that allows us to understand space-time without neglecting its quantum properties. Loop quantum gravity shows that it is possible to create a consistent theory without fundamental space and time, yet one that still allows for quantitative predictions. In this theory, space and time no longer serve as all-encompassing general forms of the world. They are approximate descriptions of quantum dynamics, which knows neither space nor time, only events and the connections between them. This is the timeless world of elementary physics. It's time to put everything together. If fundamental physics contains no single time, if all variables are, at the deepest level, on equal footing, then what is it that we call time? What do our clocks actually measure? What always runs forward and never returns? Many things in our world are not fundamental, they emerge. A cat is not part of the fundamental equations of physics. It is a complex pattern that reappears because nature allows such structures to exist. A group of children play soccer. They divide into teams, choosing players one by one. Where were those teams before the game? Nowhere. The teams emerged during the process. Up and down are not written in the equations of the universe. They are created by the Earth's gravitational field. A cloud has a sharp surface when viewed from afar, but from inside, the boundary disappears. A desk looks solid, but if we were the size of atoms, it would appear as a cloud of buzzing particles. We understand the world using concepts meaningful at our scale. We see the sky rotating around us, but in truth, we are the ones rotating. This is not an illusion. It is the reality of our relationship with the cosmos. Time emerges in exactly the same way. In the chaos of molecular motion, every variable is constantly shifting. But one thing remains constant: the total energy of an isolated system. Energy and time form a special pair. They are linked to one another. Knowing the energy of a system is, in a deep sense, knowing how time flows for that system. We usually think like Newton. Time determines energy, and energy determines the state of a system. But the same equations can be read in reverse. The macroscopic state determines the energy, and the energy determines the emergent time. Carlo Rovelli repeats the central idea of his work. Time arises from the defocus of our vision. Boltzmann discovered that thermal behavior emerges from a blurry picture because we cannot see the microscopic details. This blurriness gives rise to a privileged variable we call time. It is not evolution in time that determines a state. It is the fuzzy, coarse-grained state that gives rise to time. Mathematicians Roger Penrose and Alain Connes discovered another source of time: quantum interaction. In quantum mechanics, the order of operations matters. If you measure an electron's position and then its velocity, you get one outcome. Do it in the opposite order, and the result is different. The operations do not commute. This non-commutativity means that the order of interactions has consequences, and this order is a primitive form of time. Alain Connes showed mathematically that time defined by macroscopic states and time defined by quantum non-commutativity are two aspects of the same underlying phenomenon. Quantum uncertainty creates blurriness, Boltzmann's fuzziness, guaranteeing unpredictability, even if we measure everything we can. Two sources of blurring lie at the foundation of time: the swarm of billions of molecules in every system, quantum uncertainty itself. Blurriness is our unavoidable ignorance of the microscopic world. Physical time is ultimately an expression of our ignorance. Time is ignorance. Alain Connes once wrote a science fiction story in which the heroine, Charlotte, momentarily receives complete information about the world perception without defocusing. I was given the incredible opportunity to perceive my being globally, not at some particular moment of its existence, but as a whole. I could compare its limited space, which everyone easily accepts, with its finiteness in time, which, on the contrary, evokes so many emotions. When she returns to ordinary, blurred perception, in other words, when she returns to time, she describes the sensation like this: "It seemed to me that I was losing all the infinite information of the quantum picture, and this loss was enough to inexorably pull me into the river of time. This emergence of time felt like an intrusion, bringing confusion into my thoughts, anxiety, fear, a sense of dissolving into something external. Our blurred picture of the world singles out a variable we call thermal time. But thermal time itself does not distinguish between past and future. So where does the arrow of time, the difference so fundamental to us, come from? It comes down to one fact. The entropy of the universe was lower in the past. But why was it lower? Carlo Rovelli's answer is simple and profound. We are part of the world. We humans are fragments of a vast cosmic fresco. We interact with the universe through a very limited set of variables. Most of what happens does not affect us. The chaotic motion of molecules in a glass of water is invisible to us. Events in distant galaxies are unknown to us. This limited access to information means our picture of reality is blurred. This blurriness is at the core of Boltzmann's theory. From it arise heat, entropy, and every phenomenon we associate with the flow of time. Entropy is not an absolute quantity. It depends on what we fail to see. The same physical configuration can have high entropy for one observer and low entropy for another. It is like speed. A child runs inside a train car at walking speed relative to the train, but at 100 kilometers per hour relative to the ground. Speed is relative. Entropy is also relative. The entropy of system A relative to system B is determined by the number of configurations of A that B cannot distinguish. Once this point is clarified, a very tantalizing solution to the mystery of time's arrow will be revealed. The entropy of the entire world does not depend only on the configuration of the world itself. It also depends on how blurred the picture of the world is for us, and therefore on the variables through which we, as part of the world, participate in interactions. The initial entropy of the world seems very low to us, but the issue here is not in the world itself, but in that subset of its variables through which we, as physical systems, interact. And it is in relation to the blurring of the picture of the world that our interaction with it generates, in relation to that tiny set of variables in terms of which we describe the world, that the entropy of the universe turns out to be low. It's not that the universe existed in some special configuration in the past. It's that we ourselves and our interaction with the universe are special. We define some special properties of the macroscopic description. The low entropy of the universe at its birth, and therefore the arrow of time, owes its origin to us, not to the universe. That's the idea. Consider the daily rotation of the sky. For millennia, people believed that the entire universe revolved around the Earth. Today, we know the truth. The cosmos isn't rotating, we are. The rotation of the heavens is simply a perspective effect created by our own motion. It is not a mysterious property of the universe. Perhaps the same is true of the arrow of time. The low entropy of the past may arise from the particular way we interact with the universe. In the vastness of the cosmos, there are countless physical systems interacting through countless variables. Among them, it is almost inevitable that some systems will interact with exactly those variables that happen to take special values in the past. This is not surprising. Someone wins the lottery every week. It would be unnatural to imagine that the entire universe began in an incredibly special configuration. But there is nothing strange about parts of it being special. If such a subset exists, then, for that subset, entropy was low in the past. The second law of thermodynamics applies. Memory exists. Traces of the past accumulate. Evolution happens. Life appears. Consciousness emerges. We are part of that special subset. Why us? For the same reason that apples grow where people drink cider and grapes ripen where people drink wine. People do not drink cider because apples grow there. People drink cider where apples grow. This is an inversion of causality. Similarly, within a diverse cosmos, some systems naturally arise that interact through unusual variables, the ones that correspond to low initial entropy. Only for such systems does entropy constantly increase. Only there does the flow of time reveal itself. Only there do life, evolution, thought, and the very experience of time become possible. Only there do the apples grow from which we make our cider time. Science strives for objectivity, but we cannot ignore the observer's perspective. All our knowledge is produced from within the world. To use a map, looking at it is not enough. You must also know where you are. That is why maps begin with, "You are here." This is an example of indexicality expressions whose meaning depends on who says them and when. Words like here, now, and I change with context. We observe the universe from the inside, interacting with only a tiny fraction of all cosmic variables. We see a blurred, coarse-grained image, and this blurriness determines the effective laws that govern the world we experience. The dynamics we call time are tied to entropy, a measure of that blurriness, a measure of what we cannot see. Time, ultimately, is something that belongs more to us than to the cosmos itself. I'm not at all sure the idea presented is plausible, but I don't know a better one. Otherwise, we can only accept as a given the observed fact that entropy was very low at the beginning of our universe's life, and leave it at that. There is a law, delta S is greater than or equal to 0, formulated by Clausius. Boltzmann, who was now serving as our guide, began with its explanation. Having lost sight of this law in our search for the fundamental laws of nature, we rediscovered it as a perspective effect for certain subsystems. In school, we were taught that energy drives the world. We extract energy from oil, harvest it from the sun, split atoms. Energy turns motors, grows plants, and wakes us up in the morning. But something doesn't add up. Energy is conserved. It never appears or disappears. And if it's conserved, why must we constantly produce more of it? Why can't we use the same energy over and over again? The truth is that we have an abundance of energy, but we don't actually consume it. What drives the world is not energy, but low entropy. Consider a simple example. All forms of energy, mechanical, chemical, electrical, eventually convert into heat. Heat warms colder objects, and once it spreads out, it can no longer be concentrated again for useful work. The amount of energy stays the same, but entropy rises, and now that energy is no longer recoverable. The world functions thanks to sources of low entropy. Without low entropy, energy would simply disperse as uniform heat. The universe would reach thermal equilibrium, a state with no difference between past and future. Near Earth, we have a powerful source of low entropy. The sun, it sends us hot photons. Earth radiates cold photons back into space. The energy going out roughly equals the energy coming in. But entropy doesn't. For every hot photon we receive, Earth emits about a dozen cold ones. A single hot photon carries the same energy as a dozen cold ones, but it has lower entropy because fewer microstates correspond to a single energetic photon than to many low-energy ones. But this raises a deeper question. Where does the sun's low entropy come from? The sun formed from a cloud of gas and dust that had even lower entropy, and that cloud came from an even earlier, more ordered state. If we follow the chain backward, we arrive at the early universe, which began in a state of extraordinarily low entropy. All of cosmic history has been driven by entropy increasing from that starting point. But entropy doesn't always increase quickly. Along the way, it encounters obstacles. A pile of firewood can sit for years. It is not in a state of maximum entropy. Hydrogen and carbon atoms remain neatly arranged in the wood structure. Entropy will increase only when the structure collapses during combustion. For example, fire is an irreversible process. But a log doesn't ignite on its own. It needs a push, a match. A wood pile is like a house of cards, unstable, yet able to stand until something knocks it down. Obstacles to entropy increase are everywhere in the universe. In the early universe, matter consisted mostly of hydrogen fields. Hydrogen can fuse into helium, a process that creates higher entropy, but only when a path becomes available. That path is the ignition of a star. What ignites stars? Gravity. Gravity contracts giant clouds of hydrogen. A compressed cloud has higher entropy than a diffuse one, but compression takes millions of years. Only when the core becomes hot enough does thermonuclear fusion begin. The entire history of the universe is about the limping and bouncing growth of cosmic entropy. Its growth was neither rapid nor uniform, as things remain in place for long periods of time, held in the embrace of low entropy, a woodpile, a hydrogen cloud, etc., until something intervenes and opens the door to a process that allows entropy to make its next leap. Living things engage in similar processes that support each other. Plants capture low-entropy solar photons through photosynthesis. Animals provide themselves with low entropy by eating. Within each living cell, a complex network of chemical processes creates a structure that opens and closes doors behind which low entropy can increase. Molecules serve as catalysts, facilitating processes, or, conversely, inhibiting them. The increase in entropy in each individual process is what enables the whole to function. Life is a network of processes that increase entropy and act as catalysts for each other. It is incorrect to say that life creates ordered structures and decreases entropy. The opposite is true. Life consumes low entropy through nutrition. Life is self-organized disorder, just like the universe itself. Even ordinary phenomena around us are governed by the second law of thermodynamics. Take a stone falling to the ground. Why does it fall? We often say that it seeks a lower energy state. But why would it lose energy if energy is conserved? The real reason is that when the stone hits the ground, it warms up. Mechanical energy is converted into heat, and heat cannot be recovered back into mechanical form. Without the second law of thermodynamics, the stone would bounce forever. It is not energy, but entropy that brings the stone to rest and sets the world in motion. The continual mixing of everything, the release of order, this is what drives events and creates the history of the world. The universe is like a mountain slowly eroding and sliding into a valley. Low entropy in the past has profound consequences. It leaves traces. Lunar craters record ancient impacts. Fossils preserve the shapes of long-dead creatures. Telescopes show galaxies as they were millions of years ago. Memories accumulate in the brain. There are traces of the past everywhere, but none of the future solely because entropy was lower in the past. Leaving a trace requires something irreversible. The degradation of energy into heat. Computers heat up, brains heat up, meteorites heat the lunar surface. These irreversible processes carve the past into the present. The presence of traces from the past creates the feeling that the past is determined. The absence of traces from the future creates the feeling that the future is open. The brain can map the past but not the future. That makes us believe we can choose the future but cannot change the past. Our memory stitches together processes spread across time. In this sense, we exist in time. To understand ourselves is to reflect upon time. To understand time is to reflect upon ourselves. Your brain is a time machine. It bridges past, present, and future. It collects traces of the past to predict what comes next. And for good evolutionary reasons, organisms that could foresee the future had better chances of survival. Natural selection shaped neural structures precisely for this ability. The capacity to jump from then to now to later is the core of our mental architecture. This is the flow of time. Mind is a function of the brain. The brain operates on traces of the past stored in synapses, the junctions between neurons. Synapses form and fade, especially during sleep, leaving behind a blurred image of the past. This image is fuzzy. Millions of details enter our eyes every second, but almost none are retained. We are stories living 20 centimeters behind our eyes. For us, creatures of memory and anticipation, time is a form of interaction with the world, the source of identity. Time is not an illusion. It is real, but it is not fundamental. Time is the thermal blurring of quantum reality, visible only to someone looking from the inside. It is the cost any system pays for being part of the world rather than observing it from outside. Ultimately, the real question is not what is time, but who are we that we ask this question? We are patterns of relationships in a timeless universe, patterns that exist only because they do not know everything else. And perhaps it is precisely in this ignorance, in this incompleteness, that everything that makes us alive is born. Memory, hope, the possibility of change, the very idea that the future is unwritten. Time is not a prison. It is the gift of ignorance. Do we have the opportunity to better understand what time is? I think so. Our understanding of nature has grown dizzyingly over the centuries, and we continue to learn. We have managed to glimpse something of the nature of time. We can imagine a world without time, see, with the inner vision of our minds, the deeper structures of a reality where time as we know it does not exist, and we are beginning to see that time is us. We are this space, this illuminated clearing where traces of our memory accumulate among the tangled networks of our neurons. We are memory. We are nostalgia. We are the longing for a future we will never see. This space is time, and although it often frightens us, it is, in the end, our happiness.